Thanks for coming with this bad weather. So I think that everybody knows me, so there's no need to be introduced. So when Papadelis asked me to give a talk about our progress in the BabyMEG facility, I realized that I should, in order to provide a well-structured presentation, I should write down a list of all the projects we're running in the BabyMEG lab, and I ended up with this. And all these projects are in progress indeed. So some of them with slower and some of them with faster pace. In some of them, we're in the process of trying to publish something, some data, and most of them are with in collaboration with other people in the hospital. So my task today is like to try to give you a taste of how it looks like the stage of each one of these projects. So the first task we had to do with the BabyMEG after we established the facility, it was to test whether our claim that it provides indeed better spatial resolution and better sensitivity compared to the adult systems. And this is what we tried to do with Shiran. At the beginning, we used this dry fandom. I have presented this thing before. And then Ellis introduced me to Mukut. And then before meeting with Mukut, I didn't know that we can use fruits to assess the localization accuracy of the BabyMEG. And at least in Greece, we eat these fruits, like we don't use them for this kind of propose. So this is how it looks like watermelon. So Mukut, he was in the supermarket, he bought this watermelon. And then we test this kind, we test the EEG cup with 120 channels, and we follow the procedure we usually follow when we run experiments in the BabyMEG. So with the Cohimas, we digitize the actual locations of all these EEG channels in order to register the anatomical information with the sensor location in the BabyMEG. And the next task is to perform the MEG recordings at the end to collect data from MRI to see the anatomical structure, how it looks like inside. So we decided to place two dipolar sources. The sources they look like something like that. There were two plastic tubes. Inside of the tube there were Cooper cabling, two cables, and then we placed two dipolar sources. One was reaching up to very close to the surface of the watermelon, so it was representing a superficial source that is easy to be detected, and one more deep thalamic source that's more difficult to detect, especially with the MEG. And this is how it looks like the slide with the MRI. So this is the dipolar source right here. So we see the plastic tubes, and with the edge of here, it represents where the actual location of the source. Yes.
Sorry, because we're like infrastructure, we use a mouse pointer when we this.
Oh, okay. Like that.
Yeah.
Okay, I will try. So, and this is how we start to perform the recordings. Like it's right here how we placed the watermelon next to the BabyMEG. So as you may know, like the BabyMEG has partial coverage, so it focuses on a specific region of interest. And during these recordings, like we did the mistake that we realized later. So the location we placed the dipoles, they were not well covered by the partial coverage of our system. So and we'll see later how this will affect our findings. And then the main goal of this is like to assess in a clinical setup how accurate is the localization of the baby squid. That's why we ask help from Toby and Ivan, and they provide us with the help of Mukut some data from an epilepsy patient. So we driven the dipolar sources with interictal spike. This interictal spike from actual recording from the T8 electrode from the sensor level. So what we did, we adjust the amplitude of the generator here in order the recordings we have at the sensor level to be at the same amplitude with an actual real interictal spike. And this is the characteristics down here of how they should look like a typical interictal spike with a duration of approximately 100 milliseconds, and then followed by a slow wave and an amplitude of approximately 200 microvolts. And this is how they come, from where they come, the signal. This is data from a 10-year-old male with benign epilepsy with central temporal spikes. This is the interictal activity, and this is the portion that we use to drive our dipolar sources in the EEG inside of the funnel. And this is the how they look like, the data. This is the MEG data. We have 76 sensors, partial coverage, and this is the 128 channels, the EEG. For people who are not familiar with that, these are called butterfly plots. So we take 30 trials in this specific case, and we average them in order to increase the signal-to-noise ratio, and this is how it looks like. How it looks like the responses for the MEG and for the EEG. And this is a reconstruction of the external surface of the watermelon, and with this color we indicate the partial coverage of our system. So we see that we didn't place actually the sensor at the proper location, and we have only a few channels here that they have a magnetic flux that is outgoing, and they have they are indicated here with a red color, and most of the channels they have an ingoing activity with blue color. So we expect actually our actual location of the source was somewhere here. And we see with the full head of the EEG 120 channels, like we see very clearly how it looks like the change in the in the polarity between positive values and negative values. You see here how nicely we have covered this source. So actually, this indicates also the problem we have with the partial coverage. Like most of the time when we run actual experiments, we should be sure that we cover well the region of interest. Yes.
What is the distance of the source to the filtered?
It was around difficult to say. It was like I think 5 to the surface from the sensor array or from the
just from the surface of the watermelon and from the sensor.
2 to 3 centimeters.
2 to 3 centimeters.
If we see the watermelons right up against
yeah.
So then, what's the
I don't.
Is the sensor actually touching the watermelon?
No. The sensor array is more inside. Then after the sensor array, there's a gap between the sensor array and the plastic coverage. Okay. So the watermelon is placed next to the external surface.
Does it look like that gap thing was the EEG gap? The blue thing is the EEG gap.
Yes.
So the MEG.
So you see that then you have the EEG, and then you see what is extracted. The extracted was a more thin EEG cup, because this has around 6 millimeters, and then in addition to the 6 millimeters, I would say roughly like 1 centimeter, and then in addition to that, you have the space from the sensor array up to the surface of the watermelon.
So the distance from the sensor to the surface of the watermelon is about
couple of centimeters. Yes.
And then the 3 centimeters.
Yes. I can estimate, but like I actually didn't do that.
No,
so, but it's a good point.
Yeah.
Oh, sorry. And this is how it looks like the signal for the deep source. You see that the MEG is quite difficult to capture. The deep source is like the most, we reach the extremities of the ability for the MEG. The EEG was able to capture the deep thalamic source, and from this pattern we see, so there are people who claim that from the topography you can get a rough idea, and it's actually true, but not in all cases, like how the underlying sources they look like. So we see a more widely distributed like change in the pattern, and we know that this activity comes from the deep source. So since we failed with the MEG because of this mistake we did, I will be fair today. So then we try to assess the EEG source localization at least, and we run different source localization techniques. This is how it looks like the data from the wired minimum norm estimates. So here we see the actual location of the dipolar source, then this is the tip of the source, for the superficial, and this is the deep thalamic. And with the red, we see the activity for a specific threshold for the localization for one source and for the other. And if we see the results, like very preliminary data, like with blue, I indicate for different source localization methods the localization accuracy for the superficial source was like 5 to 10 millimeters. I'm pretty sure that with the MEG we can go much lower, like 2 millimeters. And for the deep thalamic source, we're around 23 millimeters for localization error. So this is actual location with versus the estimated locations of the MEG and the EEG. And this is the next step we'd like to do with Mukud, because this has also a very important, it's high importance like for the clinical practice, because most of the epileptologists, what they actually try to do, they try to see the localization at the seizure onset, at the peak of the seizure. Like, so we have the seizure here, and this is data from absence seizure from the epilepsy patient, and then we go to the first activity, and then we try to localize at this level where this activity comes from. And this is one of the next step with this study, including many other things. I will skip that. We'd like to run the same recordings in the full head system, Electa, then to check what's happening with less electrodes. When they have in locked monitor, they have only 20 electrodes. When we don't have localization, registration, and things like that. So,
going back to the plots here, the previous slide.
yes.
I mean, I know this is preliminary data, but it kind of looks like for the deep source, it doesn't really matter what algorithm you use, you get roughly the same localization. That's true. Is that kind of what people have assumed? Or
There are no big difference about source localizations for the methods, and this is what I have shown for the MEG in a previous paper I have published.
right?
So most of the of course, like the problem with this kind of studies, like there are people, or this kind of study are reviewed by people who develop this method, so they try to insist that my method is better than the other. But roughly speaking, like most of the methods, they perform quite well. I don't know, surprisingly, DSTM didn't perform well for the superficial source. This is somehow expectable because this specific method is made especially for deep sources. Okay. And you see here also the localization of DSTM is much, it's slightly better than the other methods. But I will not put too much emphasis on that. Like,
But also, regular M&E is biased towards corticospinal.
That's correct. But this is weighted M&E. The weighted it's weighted to the depth, so it somehow cancels this effect. So I have presented this data before. Like I would just try to. I think this study. It's we submitted papers under review right now. Like it's about a tuberous sclerosis patient, and in this patient. For people who didn't know what is tuberous sclerosis, like it's a genetic disorder that the patients they have multiple tumors in the brain, and here is the tumors they have been extracted. This specific patient had a big tumor in the right occipital parietal cortex. That was this specific tumor was calcified, and we collect data from this patient with MEG and the EEG. We identify the erectile spikes. And then we try to localize this activity. We would like to be sure that with the MEG we didn't present any findings that they are not valid. So we see now that we covered quite well the source with both with the MEG. Here we have a lot of sensors that they have positivity and a lot of sensors that have negativity. Actually, they're not called negative activity. They're called like ingoing and outgoing activity. And we see also the pattern with the EEG data. And this is how it looks like the source localization findings. So this is dipole sources across time. So in what I mean across time, like so we run dipole feeding slide by slide, millisecond by millisecond, from minus 15 milliseconds to plus 15 milliseconds from the peak of the rectal spike, and this is how the dipoles they are moving. There's no big change with the MEG. more change with the EEG, more transition with the EEG, we get quite a good high goodness of it. And the most important finding here is like always the activity was outside of the tuber, like we're not going, never going inside of the tuber, like always in the vicinity of the tuber. And we confirmed this finding, but also by single trials activity. So we ran dipole fitting in individual trials. So this is this red balls here. They indicate like it's the localization of each individual in the rectal spike, and we have a cloud that was formed for the MEG and for the EEG data. The cloud was always outside of the tuber, in the vicinity of the tuber. And we confirmed the same findings with a more distributed source localization technique that was like the minimum norm estimates. So here we see how it looks like the extraction of the tuber here, and the localization result, the average data for the dipole fitting was outside, and also the minimum norm estimate. And that was something that very few people they have done. We tried to integrate data with DTI. So we got the we defined the region of interest from the MEG, and this analysis was done. The DTI analysis was done by Banu, and so we defined different regions of interest based on the anatomy and also based on the function, or based on the epileptogenetic activity. And digging in the literature, we found that the most proper way to assess that is by defining 4 different regions of interest. One that was the actual tuber, like with green here. The other was like the cluster that was defined, or the volume that was defined by the dipole fittings from the single trials. And this is where the MEG indicates that the epileptogenetic activity comes from. And we decided we should find also some control conditions. And the control conditions, like it's from the healthy, the contralateral healthy tissue from the other hemisphere. So we find here the tuber, the cluster, then the normal tissue contralaterally, and also another volume that was like the mirroring of these 2 regions of interest on the other hemisphere. And here's how they look like: the DTI, the fibers that they pass through these volumes, and this is the values of functional anisotropy and the different values for the DTI. What is important to consider, like that we see, though we cannot speak about statistics because like it's a single case report, we see like smaller values for the functional anisotropy, like for the cluster that is located, as indicated by the MEG, and a much higher value for the ARD. And based on what we saw in the literature, like this kind of values, like they quantify the myelination of the fibers passing through these regions. Actually, like people who are DTI experts, they can correct me or improve that. So that's the conclusions, like from this patient, like data that the epileptiform activity in this patient comes from outside of the tubers, in the vicinity of the tubers, not from inside of the tuber. And actually, in order to expand this finding or to strengthen this hypothesis, like we need data from more patients. That is difficult to get, but we are trying. So I jump now to another project that.
So to take back that, otherwise, what you're showing there, the potential is that with these ones we get high localization. So when we get the single trial, we'll be able to watch that source as it moves around, if it does move around in time, and then characterize connectivity to see if we can put it all together.
Exactly. And actually, also, what the localization of the single trial levels indicates you, it gives you the confidence interval of your localization. And you can, so you know that your source is somewhere here, I would say. Then you can use this as a volume, and then you can consider this information for see what's happening in the anatomy. There are not many studies like that that they can use this approach. Like so, I don't know. We're trying to find how valid it is. Like because there are not many labs who run MEG and DTI. Like so, and.
How big was your looking for
it was like 9 nanometers, like this is another project that we ran with Dr. Harini. She sent us a couple of patients, and then it's about the high frequency oscillations in epilepsy. So there are people who claim that high frequency oscillations, they indicate a biomarker for a genetic zone inside of the brain in epilepsy children. And what we call high frequency oscillations is that activity with a frequency from 70 to 250 hertz, and even higher. Like the people, they report ripples, what they call ripples and fast ripples. And we try to see whether, because we didn't have so many data from epilepsy patients, we try to see whether we can see this activity in epilepsy, in our epilepsy patients. And we indicate that we can see this kind of activity in two patients, like both of them, they have cortical dysplasia, and one was located in the left temporal lobe. This is data from a 6-year-old child. So this is the MEG data. We see the empirical spike, and then if we filter the data in this frequency one, we see quite clearly that there's a high frequency oscillation, what they call ripple here. Though typically people, they expect the activity to be a little bit higher, like in our case was around 90 hertz to above 80, that's the definition of the high frequency oscillation, but it was like towards this, the lowest edge of this frequency range. And based on some findings in the literature, like we form a hypothesis that we believe that is valid, but we need more data to prove that. So what we observed, that was Yossi's idea actually, and we found also in the literature like how we can work on that. We saw that in some interictal spikes, they were superimposed high frequency oscillations, and some they were not. So if you see here, for example, this interictal spike with the high frequency oscillation content, and this interictal spike without high frequency oscillation. And the hypothesis that they are located in a different place, and that was the case. Like we found this with actually this is each data, not the MEG data, because we have the full head coverage. And we confirmed this with the MEG, because the MEG was focusing this activity here. So based in the literature, and this is probably the hypothesis that we built on that, is that the interictal spikes that they have high frequency oscillation superimposed on them, they have a more pathological background, so they call them as red spikes, while the interictal spikes that they don't have high frequency oscillation, they call them the green spikes. So they try to find out the clinical significance of this kind of finding. I will skip that. Then I will jump to something totally different. This is my main project, and this is I try to put most of my effort here. We try to assess the functional and structural connectivity in the brain of cerebral palsy children. And why we focus on that? Because the cerebral palsy, it's a disorder of it's a motor disorder. So most of these children, they have motor deficits, and there's a hypothesis that these deficits, they come from a functional disorganization or a reorganization in the brain of these children due to white matter lesions in the periventricular area. So in order to test this hypothesis, like this is a schematic diagram of how it looks like a healthy sensory motor network. So this is when we make any kind of movement, we grasp an object, or we move our fingers. This is the key areas that they communicate in the brain. For example, when we touch an object, we have the sensory information that comes inside of the brain and up to the primary somatosensory cortex here, and then through all this network that involves all these areas, we provide the output that is in the primary motor cortex, because we give an output, like we give movement. So we try to assess this kind of network, and our hypothesis that there will be deficits in the functional and the structural connectivity in this network in the children with cerebral palsy. And in order to do that, this is how we run our experiment. This is a hemiplegic children with cerebral palsy. Hemiplegic means that one hemisphere is affected and the other hemisphere is healthy. in this case, like this, the children, they had affected the left hemisphere. So with our partial coverage, as you see, like we ask the subject to sit, to lay down like that, and then we ask them to place their head in this position to cover the contralateral side. If the next step is to collect also data from the lateral side of it, the next stage. So we always check whether we have covered the S1 and the M1 activity. And what we do, we provide air pumps. So there is brief air pump, they come to these tubes, and then they expand this membrane, this thin membrane, and they provide sensory stimuli to the children. So in the first type of experiment, we have a pure pneumatic stimulation. So the subject, they lay down there and they receive the stimuli. And we expect to see activity in the primary somatosensory area. And in the next step, because I would like also to try to check the connectivity between the primary somatosensory and the primary motor cortex, we run another experiment that we ask the subjects when they feel a specific stimuli to respond by moving their fingers. And this is how it looks like, this experiment. So you will see, so we connect the tubes in two different fingers, in the D1, thumb, and the third finger, and then we provide the air pumps randomly, and we ask the subject to move his thumb or his finger, the corresponding finger. So if he feels the stimuli here, then should move the finger fast and sharp at the same time. Then when he feels here, then moves the other finger. And if you observe, like this subject, because of the spasticity, he has difficulties to perform the task. Like sometimes he moves the fingers together, like he has difficulties in the somatosensory processing of the information. And this is what we'll try to assess. And this is how it looks like the somatosensory evoked fields. This is data from a healthy child, a typically developed child, age mass, and this is a child with dysplasia. This is the first cortical response. We see activity in the primary somatosensory cortex, primary motor cortex, parietal. This is very expectable result based on the physiology. And then we see that the activity of cerebral palsy children is like much more diffuse, and they are in almost all the children, like they was located in a more anterior locations. So we see very few activity in the S1 in some children with CP, and we saw very strong activity in the premotor cortex and the primary motor cortex, indicate that there's a kind of functional reorganization in the brain. And the task now is how we can quantify that, because it's a very descriptive way. So we categorize the children. We have 3 children, typically developed children, 3 children with hemiplegia, one side is affected, and then we stimulate the fingers, as I said before. We see that the dyslexic children, they have less severe symptoms. We see here that there's a similarity between the typically developed child, but like the waveforms are quite different. What is interesting is that the specific hemiplegic children that you will see later in the next slide, that you see as a big lesion in the brain, there's an absence in the first cortical response. So like we provide the stimuli here, this is the first air puff here, and then there's there's no activity, like so does not receive this information at all. While in the other side, that is what we call the healthy side, the activity it's much more abnormal, and this is also in agreement with the literature that indicates that probably there's a reorganization in its lateral side of the stimuli. And this is how it looks like the source localization for the 3 different fingers. This is where the first cortical response for the thumb, for the third finger, and the little finger, D1, D3, D5. You see how nice, like in the typically developed child, we see the somatotomy here, very inconsistent with the biography. And this also has some interest in the precise evaluation epilepsy patients, because like we can localize this activity with very high accuracy. And we see here that in this specific hemiplegic patient, you see that there's a big lesion in the left hemisphere. There's almost absent activity. There's no activity in this specific hemisphere. And on the other hemisphere, for this one and also for the diplegic child, we see a reorganization of the brain. So the D1 activity was much, there's a big distance between the activity in the D1 and much more distributed. We see two different locations of activity between the D1, D3, and the D5. And the same also what we observe also from the in the healthy, supposed to be the less affected side of the hemiplegic cerebral palsy children. So these preliminary findings I would like to extend by bringing more patients to our study, indicate that there's a reorganization, functional reorganization in the brain of the cerebral palsy children, especially in the affected hemisphere. And as I said, like always, we try to link our MEG findings with the DTI findings. So Bandusi became the specialist of the DTI with the MEG lab. So this is my initial idea was like to try to track the fibers from the thalamus to the S1 for the hand area, somewhere here, and the same from the thalamus to the M1. Though it was proved much more difficult than we expected. So always we get this pattern that is in the leg projection area, but it's difficult to link what's happening in the hand area. So, and what we did, we defined the region of interest for the S1 and the M1, and then we tried to find out the fibers and the characteristics of the fibers passing between these regions. And this is how it looks like the results for the corticospinal fibers. So this is the fiber that go from the thalamus to the M1. And then for these fibers, we see quite interesting results. So we see that the affected side, the more affected side is on red, is less number of fibers. So, and also based on the findings of the FA and the RD, we see that these values, the decreased number of the FA and the increased number of the RD, indicate that there's also a problem in the myelination of these fibers. So we have also less number of fibers, but also worse quality, I would say, of fibers connecting the thalamus and the M1. Yes.
What's the big hole in the case?
So
This is the lesion.
yeah, the lesion. Yeah, the cranial stroke. Yeah. Yeah.
So this is that same kid.
Yes, it's exactly, it's this child. So here's the reconstruction of the start of the brain. This hemiplegic child. So this is how it looks like the MEG data here. This is the same patient here and here. This patient also had absent the first cortical response. So there's no functional activity when you provide the air pass. And you see also this big lesion here, and you see also how the DTI fibers here, they deviate. So there's nothing to project there actually because of the lesion.
So that's surgery.
Yes,
No, this is stroke, perineal stroke, yes.
So
yeah. Because basically that tissue just dissolves away. We didn't know them just like that forever. Some of them want to stand up around the margins.
So another the slide with these surfaces.
Here, go back. The defect is.
This one?
One of the surfaces.
The surfaces.
Yeah. More back here.
This one.
You see, there's a big hole.
So is it possible that there is activity in that episode that is just too deep for the energy?
No.
No.
Well, it wouldn't be white matter, it has to be there. Something else, right? There's no other gray matter.
Oh, that is. Yes.
So it's not a matter of like localization error. Because in any case, like you see also this activity. And also this is a nice question because like we don't know whether this activity here is a much later response on the cortex somehow, or this is a secondary process, like so the information went probably to the lateral side and then returned to to be processed from this side or from this hemisphere. I don't know. And this is how it looks like the DTI findings from the thalamus and primary somatosensory cortex. So here we don't see changes, or we don't see any changes between or differences between the number of the fibers, but we see differences in the FA value and the LD value. So although we have only 3 patients, like the data, we cannot speak about statistical significance, but like this, there's an obvious difference in the values of the FA and the LD. So we are in the process of trying to explain these findings, like why thalamus and M1 we have also differences here in the number and the quality of the fibers, but from the thalamus to S1 the number of the fibers is not affected, but what's affected like the FA and the LD values. So this is actually not the actual findings. Just I try to present how it looks like the data from the functional connectivity experiment. So this means that the subject, they are stimulated. So we provide the air path here, and then we see the first response, and then the subject moves his finger. So and at the same time we collect the EMG data. So with the EMG we know that the muscle is moving here. Then before that, there's a preparation or the command from the brain to give the motor function. So these slow waves is the motor evoked field. Like they provide the command to the muscles to move. And the task is to assess the functional connectivity. This is what we're trying to do with all the network. This is actually so we try to localize the activity in different regions of interest, and then to see how the functional connectivity looks like between all these regions. And of course, like to compare the findings between the cerebral palsy and the So our results indicate that there's a reorganization at the functional level of the kids with cerebral palsy, and this reorganization could be a result of decreased quality of thalamocortical projections due to damaged posterior thalamic radiations because of the white matter periventricular injury. So Vanushi gave me these slides like from the auditory processing in children. So this is an experiment she runs. I will go very briefly. Try to find auditory difference in the auditory response in children with autism spectrum disorder and typically developed children. So we see the first cortical response in the deep stimuli and the activity there. So she ran some time frequency analysis and try to find gamma response. So she saw some gamma nice responses for the autistic children compared to a typically developed child, and some also DTI and resting state. I will not go through all this slide because I'm pretty sure she will give a talk in more details about her findings. And this is a project we have initiated with Shiran and Rudolf a long time ago. So we try to develop a tool that is useful and accessible to everybody, user-friendly to everybody. Because like from my experience with the MEG Society or the EEG, always you have to have your own software, or the softwares they exist like they are some they support some formats, some they don't support other formats. So what we initiate as an idea, and we try to work on that despite the limited time, is to develop a web-based interactive tool that will be user-friendly, so people will easily just drag and drop the data, put them in the word browser, like, and then try to analyze it from the basic functions. And this is how it looks like, what we call the unique WebMEG, and then we agree with Hela, like better, I guess, WebDrop, to fit in the concept also of what Rudolf is trying to do. So this is how it looks like, the application. This is EEG data, 20 channels. Then you can perform the basic functions of just selecting channels, delete them, delete the bad channels, and you can filter the data. You can make some very basic processes like estimate the Vogt fields, estimate the topography, how they look like here. So this process in a very initial stage, I would say, but we are hoping that we will manage to find some time to do some kind of improvements and go further with that. So I will close with projects that actually we don't lead in the BabyMEG, but we provide some support. This is a project in collaboration with Toby and Sigrid from his lab. So this is about the electrodermal activity. This is a software that we have developed with Shiran. So what they're trying to do, they try to find out the electrodermal activity, to record the electrodermal activity and correlate it with the seizure onset zone or the activity in the EEG in epilepsy patients. So here we see the recordings of the electrodermal activity, and then our software is able to detect when we have a galvanic skin response and what they call it storms. So when there's many galvanic skin response with some criteria, then we identify that we have a storm there. And the most important thing in terms of finding is that these storms, you see here, so we have identification of these storms and these storms here, they are just preceding like a couple of minutes. It's a long recording, so like it's an hour's recording, couple of minutes of the seizure onset. So there's a storm first in the autonomous system, and then there's a seizure onset following. So we don't have the hypothesis of that, like they work on that, like just to provide the support. We built the algorithm, the software to make this kind of data analysis. And this is another project also we run with Shiran and Toby and Dr. Tasker. This is the development of a tool for what they call bar suppression in status epilepticus. The status epilepticus is a life-threatening condition like that, in which the brain is in a continuous state of persistent seizure. So what these patients are hospitalized in the intensive care unit, and what they are trying to do, they try to provide sedation drugs in order to suppress the brain and suppress the activity of the epileptic activity. But they should monitor these patients, because like they should know how many drugs they provide, and then not to provide too much drug, but at the same time to manage to control the seizure. And this is what we call here. You see, this is a pattern. This is data from a patient in the intensive care unit. So they provide the sedation agent. Then we see this activity in the EEG. This is called the bars. And then you see the suppression here, bars and suppression, bars and suppression, bars, suppression. So you should quantify this activity in order to know how much drug you should give. And this is the algorithm we have developed. You see here that we quantify the power and the frequency quantity of the signal. And you see with the B is the bars, with S is the suppression. So we identify and quantify this activity by using this algorithm. So the next step we have right now, and we would like to develop that in the pattern at the end with Tito, it's to make an online system, like to have an online reader. So we'll online read the data from the monitors in the intensive care unit, and we'll provide the nurses and the doctors this kind of information. So, of course, like all this is kind of it's a teamwork. So I hope I didn't forget somebody. So this is our team, and this is the collaborators of some of the collaborators. Okay, thanks. That's good project. Are you in? Yeah. We have done this study in Japan a long time ago in visual experiment. So we compare MEG data for functional MRI, and we overlap the activity. The first response. So this is a great project. I'd like
Did you go to the
Yes, yes.
Yeah, that's the normal patient. So, yeah, normal patient.
Yeah, that's adult normal patients.
Adult normal versus a
No, yeah.
patient with a vascular malformation or a preacher that doesn't have normal vascular response yet. So the variables.
So actually, the function MRI is a tool. It's what we would like to have because, like, what we try to do so far, and I think we are making some progress, is the combination of the MEG with the DTI. But then the function MRI can provide us like the localization, the better localization accuracy, and can tell us that indeed the function information comes from there. So this is.
Steve has done some combined work too, taking the fMRI. We're going to actually move to our goal, using the fMRI to guide
The MEG.
Yeah.
Yes.
Mm-hmm.
Yes.
Yeah, we'll see those.
This is a good idea.
Yeah.
There should be a more compatible.
The pneumatics, yes.
Yeah.
So actually, and what we realized is the MEG, what is MEG compatible is for sure function MRI compatible, but not vice versa, because the MEG is much more sensitive. So we had this problem with the camera. We checked a video projector from a company. It's quite small, so Yoshi would like to try this. So it's MRI compatible, and they have tested in MRI, but when we bring in the MEG, like it's not.
Same thing with the EEG too, right?
Same. Though they have other issues because in the MRI the gradient the magnetic field creates like can burn the amplifier, so we have other issues, but we don't have with the MEG. Okay, thanks a lot for coming. I hope the snow is not so bad outside.
Next year you can show the BabyMEG.
Excuse me?
Next year you can show the BabyMEG.
Yeah.
Maybe this fall.
Yeah, I hope so.